Okay, so this is the week we've been waiting for, finally getting to sheaves as we make our way through sheaf theory through examples. Uh, but don't want to disappoint, but to better appreciate sheaves and to better understand how they can be applied in simpler contexts, I decided to take a slight diversion for discussing bundles, which are dealt with in the Sheaves Revisited chapter and example 210 and beyond. Um, and I figured that because they articulate diagrammatic conventions and ideas that are quite central to sheaves, that would help us better understand sheaves. But as I made my way through the bundle side, I discovered that there's a sizable practical and theoretical gap that we continue to face. It's a bit of tech debt on the theory side, but in terms also of very practical components. And this actually brings us back as a topic to the discussion of universal constructions and the discussion of categories. I guess it will be in the category, the prelude to, maybe in the category chapter. And that concerns slice categories. Slice categories, we kind of zipped through the discussion of them within sheaf theory through examples. And I regretted that because they form such an important building block for many categorical constructions. They're important constructs both theoretically and in terms of practice, in terms of, for example, CATLab, and to some degree, perhaps more than I currently realize for Cat Colab. And they also are very useful in practical categorical programming. So we're going to talk first about slice categories, and I'm hoping that this won't occupy us through the entire time, but if it does, it'll be worth it because they're really, really useful practical things where there doesn't seem to be a lot of guidance on them online. And I think it's really important that within our group that people understand slice categories, how to use them, and where they fit in, and for what purposes we use them. Like what useful benefits do we secure from them? What benefits do we secure? Okay, so I'm going to be talking about slice categories and hope that we'll be able to move on to bundles, which really are intertwined with slice categories. In fact, provide notation for slice categories in a later part of this session. So I've just provided some comments on motivations for slice categories. I won't elaborate here. The intuition, one of the things that recommends slice categories is that they fulfill a very specific need and they come with a great deal of intuition around them. Okay. So I tend to think of a slice category as a slice category for some underlying category C over an object in that category X as being about annotating that category, objects of that category C, with extra information. But not only associating them with that extra information, sort of tagging it onto them, but ensuring that the morphisms in that underlying category are adapted to honor that information, to preserve that information. In other words, morphisms in the slice category are not merely any old morphism in the original category. They're the morphisms in the original category that honor that underlying information. Now, this sounds very abstract, but I think you'll get the gist of it quite quickly here. So, basic idea of a slice category is shown here. I will note that I'm concentrating here on these categories where it's C/X or C down arrow X. I believe these are called sliced. I should know. It's sliced under or sliced over. I get confused which is up, which is down. But the other is just dual to it. So it's just a flip of it. I think it is technically dual. So I'm not going to dwell on that because it's a slice over. In any case, given a category C and an object in that category C. So imagine you have a category, some underlying category, say it's set. And you have a particular object, X, in that category, particular set, right? From that information, category C and the object, we specify a slice category, C/X. Now, this slice category has as objects, this is really important. So what is this category C/X? Well, it has objects and morphisms. What are the objects? Well, they're a pair of an object in the original category C and a morphism in that original category from C to X. That morphism had to have existed in the original category. Remember, X is an object in the original category, right? X is some set. Maybe C is set, X is some set, and the objects of our set/X category are going to be sets paired with a morphism from that set to our particular set X. Okay. Now you may think, well, that's kind of weird. The objects here are an object from the virtual category in a morphism. It may seem like oil and water, but it's not. It's a very particular morphism. It's a morphism that says sort of how to map C's information into our X. It's it'll be a very particular function mapping from any old set into our set X. Okay. Now those are the objects in this slice category. What are the morphisms? Well, the morphisms are commuting triangles. That may really throw you, but bear me out here, and you'll see that it makes a world of sense. We're specifying they be commuting triangles fundamentally because we care about we want morphisms. We want as morphisms only things that honor this mapping to X, honor the annotation with X, okay? So we're going to be concerned about things where, for each object in our category, say in set, we have a mapping that tells what maps to each component of X. And we want as morphisms things that preserve that information. So if we have a morphism from C to D in C, in the original category C, from object C, say from one set to another. In order for there to be a morphism in the slice category, that new object that it maps to has to itself have a mapping to X that is compatible with this original mapping. So if we take C and we transform it into D, the things that we transform, so if we have a given element, call it A of inside C, an element of our set, and we map it to an element A prime in D, Right? If these are sets, imagine we have an element A here. We map it to an element in D, set D, A prime, and then we map that to X. That has to go to the same element of X that A would have gone to here, because it has to commute. If we do this and this, it has to be the same as this. So we have A, and it goes to A prime, and then we map to X. That has to be the same as mapping A to X. Now, again, this may seem weirdly technical. How can that be a morphism? Well, look, I mean, if you think about composing them, C to D and D to E, then there would just be a bigger commuting triangle with E down to X such that both steps of it commute, right? And therefore the whole thing commutes. You'd have another commuting triangle here, and if you went like this down to X, it'll be the same as going like this to X. So it kind of makes sense. You can imagine identity, C to C, and then to X. That's going to be a degenerate form of a sort of trivial form of that commuting triangle. But this may seem just weirdly Baroque, but let's think about it. Again, this is saying that basically in this slice category, we have this extra annotation information X. And every object in C for the slice category, we take every object in C and we annotate each part of it with information from X. We sort of label it with information from X. And the morphisms in the slice category are just those morphisms from C that honor that information, that honor that annotation. So again, if we have an annotation on a part of C, because it's mapped to X, that tells us our annotation on a part of C. And we map that part of C to D, and then map to X, that has to be the same as the original annotation, or the morphism just doesn't exist in the category C over X. The only morphisms in the category C over X are the structure-preserving mappings. Remember, this is a theory that goes all through category theory, right? When you have a category, whether you don't really see it as much. It's like a fish not knowing they're in water with category set because there's no structure to be preserved. But if you get a monoids and you consider the category of monoids, the morphisms are monoids and the objects are monoids and the morphisms are monoid homomorphisms, right? If you go to graphs, the objects are graphs and the morphisms are graph homomorphisms. If you go to causal loop diagrams, the objects are causal loop diagrams and the morphisms are causal loop diagram homomorphisms, these sort of structure preserving mappings. And so it is here. We are lending the category C structure by giving it annotations, and the morphisms are therefore have to honor that information, that annotation information. Okay, let's go through a little example. And again, I think we can avoid this taking even most of our time today. Okay, so you'll recall the schema graph, right? Remember that? This is our schema. Remember that? We have edge, vertex, source, and target. Remember that? And do you remember how we encoded a graph, right? What do we do to encode a graph with this schema? We had a functor from this into what? Begins with S, ends with T. Set. Yeah. Okay, so E goes to a set of what? Edges. V goes to a set of vertices. Source goes to a function from the set of edges, so to a set of vertices that specify the source for each edge. You know the shtick. Okay, now I am going to now have a particular encoding of this. E is going to go to a two-element set. So this is some instantiation of this, right? This is C set. E goes to the set of plus and minus. That's a set. We just label it plus minus. These are just ASCII characters. Okay. V goes to just a one-element set. I don't care what you call it. Elephant, flower, rock, whatever. source goes to the only mapping that it can go to, right? It's unique, right? David Spivak would have labeled it with an exclamation point, as would John Bias. Plus goes to the only object it can, minus for source maps, sorry, plus to this, minus to the same thing. Target maps this to that, minus to the same thing, right? Right. In other words, these are unique. I mean, they're unique. They're totally defined. They're trivial. I mean, there's no information. They are what they have to be, right? Okay. Now, this is a C set. What is its encoded graph? Just to make us thinking in terms of graph encodings. What's its graph? What graph is encoded by this? This is a C set. What's the graph? What does it look like? How many edges does it have? How many vertices does it have? One vertex, two edges. What are the two edges? One's called plus, one's called minus, right? This is what it looks like right there, right? We good with this? Okay. This is going to be really important for the next step. Keeping in mind this ability to go between these representations. Okay. So to take us to the next step, you'll recall the category graph, right? Right? What are the objects here? They're graphs. What are the morphisms? Graph homomorphism, right? Okay. We are going to slice this category over a particular graph. Remember when I said if we slice the category C, we slice it over an object in that category. The object here, well, it's an object, therefore it's a particular graph. Are you comfortable with that? We're going to slice it over a particular graph. So remember when I talked about a slice category, what are the objects going to be here then? Remember what they are in a slice category. So what are the objects here? Yeah, they're a pair of graph and a morphism, right? And a homomorphism. Yeah, homomorphism between graphs. Right. That's important that we remember it's a homomorphism between graphs. It's a structure preserving mapping between graphs, right? Okay. So those are going to be our objects, and morphisms are going to be structure preserving mappings. Now, we're going to take the position here, and this is important, that each of these objects, which is a pair of a graph and a morphism, it's going to be a graph from that morphism, excuse me, it's going to be a morphism from that graph into our selected graph X, right? In a slice category, we're selecting a particular X, particular graph, right? There's going to be one graph right here, which we're going to be mapping. We're going to be annotating all these graphs with that information of the graph as encoded by the homomorphism. Do you remember that? Remember I said this just here? That each object is in our slice category, is an object in the original category, and a mapping here from that into our designated object. And I said this served to annotate this. Each of the pieces of this is annotated with this information. And that's exactly what we're going to do. Here, this will be a graph. And we're going to annotate each graph with the information encoded in the graph, with this being what? What is a morphism in this category? Graph homomorphism. So we're going to sort of map it in, and that's going to annotate the pieces of this. Okay, so this may sound a little bit weird, but okay, so right. Okay, somehow my key slide disappeared. Hey, where's my key slide here? I had a nice slide. Okay, now I'm really in trouble. Okay, well, I'll recreate it. It disappeared, but I'll recreate it. There it is. We're gonna, hey, okay. Oh gosh. Okay, here it is. I don't know what's going on. Okay. So instead of this, what we're gonna have is this. Okay, sorry about that. There we go. We're gonna get rid of this. Okay. So within the category of graphs, let's consider a morphism, right? From graph C to graph D. Mm-hmm. And this is going to be our designated graph. If this is our designated graph, this one right here is our designated graph. What is this morphism here, this graph homomorphism going to do? What is it going to do? Well, first of all, think about this as a graph, right? This is maybe it's some god-awful big graph. Maybe it's a small graph. Where do the vertices of this graph have to go to with this graph form? The only vertex, right? So there's no distinctions made between the vertices. There's no meaningful information annotated by the vertices. What are the edges of this labeled by?
One map to plot.
One map to, yeah. So a particular graph homomorphism will map some edges to plus and some to minus. Mm-hmm. And so what this is going to do is annotate this graph with polarities. Do you see that? Okay, now you may say, well, okay, yeah, okay. But what's more interesting than that, yeah, it is, if we have another graph D, and it's annotated with polarities. Its edges are annotated with polarities, right? Now, for this triangle to commute, this homomorphism has to do what? Can it, normally this would be a graph homomorphism. Any edge could be mapped to any edge from the same target vertex, right? So if we had an edge between vertex A and vertex B inside of C, it's kind of fun game, like, and it could map to any edge between F of A and F of B when we map over here, right? This is called that. But now, can it map any edge to any edge and still keep this triangle commuting? No, it has to map what? So if C is annotated, the edges in graph C are annotated to plus minus. The edges in graph D are annotated to plus and minus. What does this morphism have to do to make this triangle commute?
Edges that would have gone from C to plus into,
yes,
that would go from D to plus.
That's right. That's right. So plus edges in C have to map to plus edges in D, right? Minus edges in C have to map to minus edges in D. Mm-hmm. Is there any constraint on vertices? Well, okay, is there an added constraint here on vertices because of this? No, there's no added constraint because they're undifferentiated, right? They all go to star. Hmm? Okay, maybe since you seem to, as hoped, but it's really good, be getting the gist of this, maybe I will ask, what if we had a thing where this was real numbers? Instead of plus minus, it was reals, the set of real numbers. Maybe we think of them as weights on a graph. Maybe it's non-negative weight reals. Well, here we'll be annotating the edges with what? Real numbers, right? And this mapping would have to map only things of one weight into things of another weight here, right? So it could deform this graph, collapse things, collapse vertices down as long as it preserved the weights of edges. As long as it honored the weight of edges. Like if this were embedded in this, it would have to have the same weights here. Do you get that notion? Okay, let's look at this. Okay, so this is our graph schema. This is a particular CSAT. It's a particular instance of the schema, right? Here we have maybe vertices marked by sort of immigration status. People here on visas. I was here on a visa for a while. Permanent resident. I was here on permanent resident for a while, and citizen. That's unfortunate, my current characterization. Okay, this is for vertices. This is for edges. We have 3 edges, such that the source of RC and the target of RC are C, source of PR and the target of PR, etc. It looks like this. This is the encoded version. Okay, now what would this allow for morphisms? Well, what would it do for a given object, a given graph in the original category, given object in the original category? What would it encode for the graph? Yeah, so it would indicate the immigration status of each vertex. Is there any constraint on edges? No. There's no, sorry. Okay, we have to be careful. Sorry. So what graphs would this allow? This is actually interesting. I should have thought this example through more. What would this allow? Gosh, that's interesting.
Each vertex of C must be one of C, like C or PR or V.
Yeah, I think it would only allow connected components. Like you could only have citizens connected with other citizens, and PRs connect with other PRs.
The citizen will get married with the citizen. PR
That's right. So if we wanted to modify it to allow every vertex to be labeled by citizenship, by immigration status, but for them to be connected with people of other citizenship, what would we have to do? How would we have to modify this? I think, what would you need?
One from C to PR.
Yeah, one from C to PR, one from C to V, one from PR to C, one from PR to V, one from V to C, one from V to PR, right?
Yeah, but the add should be in a set of add. You only have 3 options, right? RC, RPR.
Yeah, but I'm saying we could add those edges, right? Between them. And that would allow a graph where every vertex is labeled as one of these 3, but every edge type is supported between these. There'd be no constraints from edges. Right? There'd be no, in other words, you could map any edge from the original graph to an edge in this graph without worrying that, both have to be both of the vertices on both sides have to be the same type, have to be citizen, have to be PR, have to be visa. So if we were to encode this, we could we could have this V, PR, and C, and it'll be a fully connected graph between them. And then you have these self edges that would encode connections of a person to their own, others of their own citizenship or their own immigration. Okay. But I hope you're getting the picture here that slice categories, again, the big picture, they allow annotation. So slice category on a category C with an object from that category C allows annotating the objects of that category C with information indicated from that original, from that category, that object C, that object X. And allows you to only allow morphisms that honor that information, that preserve that information. And this allows a certain modularity of, in terms of adding on features to a category in terms of annotations and making sure those annotations are preserved. Okay. Now, there's a lot more nifty things you can do with slice categories, particularly when you start slicing over the category cat. And morphisms, so morphisms in this category are then functors that honor composition. This allows us to have slice categories that implement, for example, signed categories. So if our original category C was cat, the category of small categories, and we have a particular object in C that looks like this, where this is an object, this is a morphism we call plus. Actually, it's the ID morphism. This is the morphism we call minus. It's an extra morphism we call F. And we have these triangles. C is now a category, and every object of the category goes to the only object of the target category X. But morphisms here are labeled with plus and minus. And then you have a composition rule for this category where minus becomes what? Plus. And where plus, well, this is ID and minus composed to minus. And minus and ID are minus, right? Plus, ID is ID, right? And here, this is how you get slice categories. Or sorry, how you get categories with polarities for morphisms. These morphisms, these functors between categories, are just those that honor that information. So we can map one category into another via functor only if we map compatible things to compatible things, like minus morphisms to minus morphisms, because it has to compose this way. So this is a glimpse of slice categories. There's more to be said about them. You can implement CatLab's attributes using slice categories, for example. So attributes for to label objects, sort of annotate them with certain types of information like real numbers or what have you, or floating point approximations there too. But I think this is all we'll touch on before we get on to bundles. Any questions on slice categories? Okay. If any questions? Okay, that was the briefest glimpse, but I think will provide us what we need